Hey guys, Mr. Bowman again. This is our third and final video for the practice assessment on amusement rides. And what we've got is we've got task 3, and basically engineers want to use the final section of our ride for other proposals. However, different companies are going to have different height requirements for the final section of the ride. So that's a really key thing, different height requirements. What we need to do is we need to generalize a model for the final section for any given amount of height. We need to justify the choice of the generalized model by linking features of the model to context. And then we need to define any variables that are used within the generalized model. And in my view, hidden within that justifying the choice of the model is a consideration of any assumptions that we needed to make our model work, and any limitations with the model, or any potential issues that could come up should it be used. So what I'm going to do is I'm going to pause the video. We're going to link back to our other one, and we're going to get into this question. Okay, we're unpaused, and we are now looking at task 3, which is to do with the generalization. Okay, so on the right-hand side, I've got my cool green addition to the ride. It's taller, it's faster, the drop is steeper. I think it's a really entertaining finish to it. And what the question needed for us was, we did need to justify the choice of model. So this is our to-do list, so to speak, for this section. We did need to define the variables, define variables. We did need to create a generalization or generalized model. That was the important part. And then after that, we did need to consider any assumptions that are required to make that generalized model work for other amusement parks. And we did need to look at any limitations or issues that could arise with that model that we've chosen. So we're going to start off with that first bit, justify. So justify the choice of our model. So what this means is we need to think of all the types of models that we could have used, and we need to explain why we chose or didn't choose to use them. So let's write these all down. So we could have had a linear model, could have been a parabola, could have been a cubic, a hyperbole or hyperbola, could have been a log graph, could have been exponential, could have been a square root graph, could have been an absolute value graph. That was one of the ones that we just looked at, absolute value. And finally, it could have been some of the trig graphs, and I'm going to split the trig ones up to, it could have been a cosine or sine graph, or it could have been a tangent graph. So they're all the options it could have been, and we need to sort through all of these ones, why did we end up with this trig function as opposed to the other choices that we had. So the first step that I wanted to think, so the part of the criteria is just the nature of what we're working with. So if you look at the end of section 5, it's sharply increasing to 0.51, 5. So we should probably write that down. So at the end of the previous section, at the end of the previous section, the roller coaster is sharply increasing. And that's at 0.51. That's that start point. And because the roller coaster is increasing, we have to use a model that increases it. So as the roller coaster is increasing, it must eventually come back down to the ground level to finish at 70,5. So what I'm just recognizing is we are going up. To get here, at some point we have to go down, and not all models can actually return back to the ground. So if you think of a log graph or an exponential graph, we'll go with the exponential, that just keeps going up and up and up. It doesn't return back down to the graph, so it's just not an appropriate model to use. And conversely, some graphs that only go down, they're not appropriate to use as well. So based on that, I was looking through my list. I was like, well, linear, they can't go down. Parabolas can, cubics can, hyperboles can't, logs can't, exponentials can't, square roots can't, absolute values can, cosine and sine can, and trig, they can't really return back to the ground. For that reason, all of those crosses, it's just not possible. So for this reason, linear, exponential, log, tan graphs, square roots, and hyperbolas or hyperboles are not appropriate because they will not be able to return to the ground after the increase. Okay, so for that reason, we've actually eliminated most of ours. So gone, 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 and gone. So we're now left with 4 of the choices. Now what we need to do is we now need to consider, well, what is the next criteria, and will any of the models not fit that criteria? Okay, the next factor I'm wanting to consider was kind of the purpose of it. It was that idea of an entertainment factor. So we're left with our 4 models, parabola, cubic, absolute value, trig. We need to think, well, which of these are going to be entertaining or which of them won't be? And when you think of entertainment value, we were really keen on that underground VR finish or finale. So what we need to think is we need to think which model is going to go up. It's going to go down, down so much it goes below ground level, and then back up. Okay, so let's kind of get this into words. So our design aimed to improve the entertainment value of the roller coaster by including an underground VR tunnel. As a result, models would only be appropriate where they would be able to go below ground level and return to the ground level. So what that's saying is our model, it must go into a negative y value, and it then must be able to return back, sorry, negative y value, and then must be able to return back to x, or to y equals 0. So if you ever think about our models, so visually, our models would look like the below. So I'm just going to get some examples drawn. So the first one on our list was a parabola. So start and finish, and you'd see there wouldn't be any underground element to that. And then the next one was an absolute value graph, start and finish. And again, you'll see there's no underground element to that. And you'll see a trig graph, start and finish. And then below that, we'll draw a cubic as well. So cubics, they can be pretty fluid or pretty kind of S-shaped, we'll call them. So that would provide for a start and finish point as well. So let's use a different pen color just to label all of these. Actually, we'll just keep on the same pen. So that there would have been a parabola, absolute value, trig, and that there would have been cos or sine, either of those, not tan though, and then that there would have been a cubic. Okay, as we can see, parabolas and absolute value graphs would not be able to go below ground level and then return back to the ground level. As a result, they would not be an appropriate model. Appropriate models. Okay, so we've now eliminated the parabola and absolute values. If we go back up to our initial list, so that's across, cubics are still good, absolute values, they're across, and trig graphs still good. So we're going to cross out absolute value, we're going to cross out parabola, and we're now basically left to decide, well, which one is going to be a better representation of the functionality of the model that we're trying to look for. Okay, so holistically, it appears that a cubic model or a trig, and that's cosine or sine model, would be appropriate choices. I think for me, the deciding factor is the symmetricality, or like the symmetrical nature of the trig function. It's very consistent, it's smooth, it goes up and down. The height is the same as the maximum, and that kind of certainty gives us a better or it just gives us a more reliable model. So let's write that. So that leaves us with the trig and cubic models, in my view. So as the cubics are not as symmetrical as trig, and that's cos angle or sine angle functions. I imagine the construction cost or design costs would be greater than a trig function. And that was because the kind of the maximum that will be a lot higher than the minimum, and that idea of symmetry, the lack of consistency, it may mean there might be additional costs associated with constructing it or designing it. And so I just realized I wrote design, but that should be design cost. Okay. And then the last thing is, well, we did have to decide between sine as opposed to cosine. Between sine angle and cosine angle, I elected to use sine angle as it starts at point 0, 0. I could easily move this point right to 51, 0. And then therefore a sine angle function would be the most appropriate model for the final section of the roller coaster. And then we're just going to write our model down here. So our model was 10 sine 360 divided by 19 x minus 51, comma here. So, and don't forget, we have justified the more individual components of it. So we knew that was 10 because of the amplitude discussed in task 2. We knew that was 360 divided by 19 because it took 19 minutes for a full rotation to happen. And we knew that was negative 51 because of the x-intercept at positive 51, 0. And finally, we just justified why it was sine. So for me, that looks like we've now fully justified our model. So let's have a look at the next step. Let's scroll back up. What else do we need to do for this part? So we've justified the model, which was the big part. Let's change pen colors now. Let's move to orange. So we now need to define the variables. We need to generalize the model, and we need to discuss assumptions and limitations. So what I'm going to do is I'm going to give a new title. So generalized model is basically the theme of this part. And the first thing we need to do is we need to discuss what are we generalizing and what variable or what mathematical pronumeral are we going to give that. So our design may be used in other amusement parks. So again, just adding in the context. However, each park may have different desired maximum heights. And I'm going to put maximum heights in quote marks there because that's kind of alluding to the variable that I'm looking to define. For my generalized model, H will denote the desired maximum height of other, desired maximum height, well, we'll probably leave it there actually, desired maximum height. And just going to note, always mention the units in meters. So we're looking at meters here. So in meters. So let's have a think of a graph. So our model, the starting point, well, we're going to have to assume the starting point's the same. And we're going to have to assume the end point is the same. And what we're going to do is we're going to go through this, we're going to go through this. We're going to assume the y-intercept, or sorry, the second x-intercept is still the same. And that was at 60,5. And the things that we aren't going to know, so we're going to know that the maximum, it still is going to have an x-coordinate of that, but we don't know what the height is going to be. So I'm going to call that comma h. And we know the minimum 65.25, and we know that's going to be negative h. So that's the point of generalization. We don't know what the height is, so we put in those pro numerals to assist us. But we have made tons of assumptions. So we're assuming the roller coaster or future roller coasters that it gets used in. It has to start at 51 meters, has to start at 70 meters, has to go underground at 60.5 meters. So just make that a bit better. So it's 60.5, 0, and the maximums have to be at 55.75, and the minimum has to be at 65.25 minutes. So all of those need to happen. But we can go through with the rest of the formula. Now, in our original formula, we had it up top here, we had the 10. We don't know what the 10 is, but we do know the amplitude is now 10. So in our generalized model, the amplitude will now be h. And we don't know how long that is. Will now be h meters. So let's change pen colors to make sure we get our formula correct. So if you have a think of the general formula, A is equal to, we're sticking with sine, B x plus c plus d. So we're going to go through and substitute that. So d is still 0 because it hasn't really been lifted up or down below or above ground level. C is now going to be, or still going to be negative 51 because we moved that from 0, 0 to 51, 0. B is the rotation that it takes, or how long it takes to complete that cycle. And B is still going to be 360 divided by 19. But just want to note, if you were doing radians, that would have been 2 pi over 19. And A is the thing that's changing because we don't know what the amplitude is now, but we do know it's denoted by H. So that would now be there. So we can write down our generalized formula. So our generalized formula, H times sine 360 divided by 19, x minus 51 would be our generalized formula. So let's write that down. Generalized formula. And that is the third of our points in our little checklist that we've got up the top here. So we've defined our variable and we've got our generalized formula now. And we now need to think of the assumptions. So if someone was to use this model and construct it blindly without knowing everything, we now need to think, well, what have we assumed? What's going to happen? So we made actually implicitly quite a few assumptions. So let's change pen color here. So let's move to the purple pen. Okay, so in using this model, we have made the following assumptions. Normally what I do is I like to bullet point my assumptions because they often tend to be single thoughts and a few short, sharp ones. So the first assumption is it must, new sections. So new sections built under this model must start after 51 minutes. And be on the ground level. They must also finish after 70 minutes at ground level. And where that assumption is relevant, so if you have a think about a ground, so obviously it works if your ground is flat, but what happens if you're building an amusement park on a slight hill? So you'd want to start here and finish here. Those have different heights. So the topography of the ground may not be appropriate. So topography just means how the land is set up. So the topography of the ground dash site may not be flat and may not allow for this. So that's a first assumption, and that's a biggie as well. Okay, the next assumption, it does relate to the middle x-intercept and the minimums and the maximums. The new amusement park, they must be happy that the minimum, second x-intercept in the middle, and the maximum, all of them must be at 55.75, 50.5, and 55.25 minutes. Non-negotiable, that's what it needs to be. So that's our assumption. So we're assuming so the other amusement parks must not want to change the timing of the maximum. That's at, how high was that? So 55.75 minutes. So the minimum as well. That was 65.25 minutes. Oh, alrighty, minimum. Minutes. And the beginning of the underground VR tunnel at 60.5 minutes. So basically, if they're wanting any change to any of those three features, our model would not be appropriate. So any of these three features our model would not be appropriate. Okay, so let's try to think of a third assumption. I normally like to do three assumptions because it normally caps it up pretty well. So we've assumed the start and end point. We've assumed the minimum, x-intercept, and maximum. And the other assumption that we need to make is we relied heavily on the idea that the previous section was increasing. If the previous section of other roller coasters maybe it was say going downwards or maybe it was flat, the design of the model just wouldn't fit and it wouldn't suit. So we're assuming that our model will like physically be able to join up with the previous section of other roller coaster rides. So our model was based on the incline at the end of section 5. And that was the black section. If the other roller coasters had different previous sections, our model may not be appropriate. And that's to say we are assuming the previous section is inclining towards 51, 0. So that is, we are assuming the previous section is inclining towards 51, 0. So if that incline isn't present, our model will not work. So I think those are three assumptions that suit the context quite well. And our final part, so let's go all the way up to our top. What else do we need to do? So we've done our assumptions, and the last step is what limitations could come up. So what problems do we foresee with our model? Let's use the red pen to do that. Okay, so our generalized model relies on H. That's being desired maximum height. Okay, and I think the big issue is if you think about our model, if we change the height, so let's say that's 10, if we change the height to 15, the height goes up, but the other thing is the minimum goes down further. And that could be a big issue given the ground. So you may have capacity to go up, but there may be utilities or other construction reasons that you can't go down any further. So a change in height will actually impact the depth or the minimum, and that may cause other issues. So let's draw that a bit more detailed. So let's try to explain that. So a change in height will cause, well, actually, a change in desired maximum height will cause a change in the minimum of the, so let's just square that off so we know, of the VR, of the underground VR tunnel. There was a see examples below just to explain this a bit more. So we've got our first graph. So red maximum height of 10 meters. So let's change pen colors. Let's go for blue. And we'll call that 15 meters. So if that goes up to 15 meters, that goes down, that minimum also goes up. And that becomes negative 15. And conversely, let's get the maximum set up there, 10, 10. And similarly, if we change it to maybe 5, just realized I didn't put a negative sign in front of the negative 10 there. So if we change that to 5, it would have an impact on the minimum or make it smaller and bigger. So the issues with this is there may be reasons why that might not change. So for example, the tunnel does need a certain level of depth or a minimum for it to be feasible, for it to actually go underground. So that could cause a few issues. So let's try to get this into words. So these examples demonstrate that an increase in desired maximum height will cause a deeper minimum. And then conversely, a decrease in the desired height will cause a shallower minimum. This could cause a number of practical issues in real life. For example, we may not be able to go any deeper because of utilities, and that's a fancy way of saying stuff like power lines, sewage pipes, etc. So stuff like that. So if we have those wires sitting at that 11 meter mark, we won't be able to dig any deeper, and that means the maximum wouldn't be possible. So I think that recaps that part. So let's go up to our top for this section. We've now just listed our limitations. And to me, that looks like we've wrapped up our answer for the excellence generalization type part. So let's have a look at what we've done. So we've gone through all of the models. We've stated kind of that a lot of the models aren't appropriate because we can't get them to start and finish at the desired points. We've also chatted about why some models are better in terms of the entertainment value. And we've then made a decision or a choice as to what the model we used was, and that was that sine function. We've then come up with a generalized model. So we've defined h as the maximum or the desired maximum height. And let's actually make a bit of improvement while we're here of the new section. So just making a bit of improvement there. For that, h will be denoted as the desired maximum height in meters. Our generalized model, the only thing that's changed from our model in question 2 is the amplitude is now h meters, and we've updated that in our formula. The formula relies on a number of assumptions. For example, other roller coasters, they must be looking to start the section at the 51-minute mark, and they must be looking to finish it at the 70-minute mark, both of them at ground level. If the topography of the site isn't flat, it may not be appropriate. The minimum, maximum, and underground, or the other x-intercept that gets to the underground VR tunnel, they are very fixed at those times. They cannot be changed. So if you're wanting to make any change to the timing of those, that's not appropriate. And the last one is there must be an incline from section 5 or the section preceding this part. If that incline isn't there, the model doesn't really work again. And finally, we chatted about, well, what could go wrong? We really heavily rely on h. And as we change h, while the maximum height goes up, the minimum height also changes as well. And that change in minimum might be an unintended consequence that might not work or might have issues in the real world. So hopefully you found this video useful. This was a recap of the excellence questions, and good luck for your internal when you sit them.